Code section 250.81 pertains to the grounding electrode system. An effective grounding electrode system is a network of electrodes providing a low impedance path for fault currents to flow to earth. Code section 250.83 addresses grounding electrode resistance. The resistance of the grounding electrode system should not exceed 25 ohms where the supply conductor has a voltage to ground not exceeding 150 volts. Code section 250.84 discusses multiple electrodes. When a single electrode, such as a rod, pipe, or plate, does not have a resistance to ground of 25 ohms or less, it must be augmented by one additional electrode. The additional electrode must not be less than 6 feet or 1.83 meters apart. The addition of a cold water pipe buried in the earth can meet the requirement of code section 250.84 for an additional electrode. It's crucial to ensure the cold water pipe is electrically connected to the grounding electrode system to be effective. The code doesn't specify a minimum resistance for the entire grounding electrode system. The grounding electrode system must be adequate to ensure that ground fault currents can flow to earth with sufficient magnitude and duration to operate protective devices, such as circuit breakers or fuses. Consider this scenario. Firstly, the resistance of the rod is 280 ohms. Secondly, the resistance of the cold water pipe is 192 ohms. Thirdly, the resistance of the entire system is 2.8 ohms. This resistance value, 2.8 ohms, is well below the allowable limit of 25 ohms and is therefore acceptable. In the scenario provided, the addition of a cold water pipe more than 10 feet away and more than 10 feet in length, buried in the earth, would meet the requirement of code section 250.84 for an additional electrode. The resistance of the entire grounding electrode system, being 2.8 ohms, is acceptable and meets the code requirements. For a grounding electrode system to function effectively, several key factors must be considered. Firstly, the material and size of the grounding electrodes are critical. Ground rods, typically made of copper or copper-clad steel, should be of sufficient length to penetrate the earth to a depth where the soil's moisture content is relatively constant. The diameter of the rod also plays a role in its ability to dissipate fault current. Secondly, the connection of the grounding electrode to the grounding electrode conductor must be secure and corrosion resistant. This connection is a critical link in the grounding path and must be properly made to ensure a low impedance path for fault current. Thirdly, the soil conditions surrounding the grounding electrode significantly impact its resistance to ground. Soil resistivity varies depending on factors such as moisture content, temperature, and mineral composition. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or soil amendments to reduce the overall resistance of the grounding system. Fourthly, the location of the grounding electrode relative to other underground metallic structures, such as water pipes and gas lines, can affect its performance. Stray currents can flow through these structures, potentially causing corrosion or interference with other electrical systems. Proper bonding and isolation techniques may be necessary to mitigate these effects. Fifthly, regular inspection and testing of the grounding electrode system are essential to ensure its continued effectiveness. Ground resistance measurements should be taken periodically to verify that the resistance to ground remains within acceptable limits. Any signs of corrosion or damage to the grounding electrodes or connections should be promptly addressed. Considering the specifics of code sections 250.81, 250.83, and 250.84 helps in designing and maintaining a safe and reliable grounding system. Code section 250.81 outlines the requirements for the grounding electrode system, emphasizing the need for a low impedance path to earth. This section highlights the importance of using approved grounding electrodes and making proper connections. Code section 250.83 provides guidance on grounding electrode resistance, specifying the maximum allowable resistance to ground for systems with voltages up to 150 volts to ground. This section also allows for the use of supplementary grounding electrodes if the required resistance cannot be achieved with a single electrode. Code section 250.84 addresses the use of multiple electrodes, mandating the use of an additional electrode when a single electrode does not meet the resistance requirements. This section also specifies the minimum spacing between multiple electrodes to ensure their effectiveness. When evaluating whether a cold water pipe qualifies as an additional electrode under Code Section 250.84, it is essential to consider the following factors. Firstly, the cold water pipe must be metallic and in direct contact with the earth for at least 10 feet. Secondly, the cold water pipe must be electrically continuous throughout its length. Thirdly, the cold water pipe must be connected to the grounding electrode system with a suitable bonding jumper. Fourthly, the cold water pipe must be free from any insulating coatings or wraps that could impede its ability to conduct fault current. If the cold water pipe meets these criteria, it can be considered an acceptable additional electrode under Code Section 250.84. Regarding resistance requirements for grounding electrode systems, the code does not specify a minimum resistance value. The primary goal of the grounding system is to provide a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices. While a lower resistance to ground is generally desirable, it is not always feasible to achieve in all soil conditions. As long as the grounding system is properly designed and installed, and the resistance to ground is within acceptable limits, it should provide adequate protection against electrical shock hazards. Acceptable limits are below 25 ohms where the supply conductor has a voltage to ground not exceeding 150 volts. In summary, understanding and applying the requirements of Code Sections 250.81, 250.83, and 250.84 is crucial for ensuring the safety and reliability of electrical systems. By carefully considering the factors discussed above, electrical professionals can design and install grounding systems that effectively protect against electrical shock hazards and equipment damage. Proper grounding practices are essential for maintaining a safe electrical environment in residential, commercial, and industrial settings. To further clarify the requirements and considerations related to grounding electrode systems, let's delve into some additional aspects. Firstly, the use of concrete encased electrodes, often referred to as UFA grounds, is a common practice in new construction. A concrete encased electrode consists of at least 20 feet of bare copper conductor encased in concrete that is in direct contact with the earth. This type of electrode can provide a very low resistance path to ground, especially in areas with poor soil conditions. Secondly, the use of ground rings is another effective method for improving the performance of grounding systems. A ground ring consists of a bare copper conductor buried in a continuous loop around the perimeter of a building or structure. The ground ring provides a large surface area for dissipating fault current and can help to equalize ground potential across the site. Thirdly, the selection of the appropriate grounding electrode conductor size is crucial for ensuring the integrity of the grounding system. The grounding electrode conductor must be sized according to the requirements of the National Electrical Code, based on the size of the service entrance conductors. An undersized grounding electrode conductor can limit the amount of fault current that can flow to ground, potentially delaying the operation of overcurrent protective devices. Fourthly, the bonding of metallic components within the electrical system is essential for minimizing the risk of electrical shock hazards. All metallic enclosures, raceways, and equipment must be properly bonded together to create a continuous electrical path to ground. This bonding helps to ensure that any fault current will flow back to the source through the grounding system rather than through a person who comes into contact with the energized metal. Fifthly, the use of surge protective devices, or SPDs, can help to protect sensitive electronic equipment from damage caused by voltage surges. SPD are designed to divert surge current to ground, thereby preventing it from reaching the protected equipment. SPD should be installed at the service entrance and at any other points in the electrical system where surge protection is needed. Sixthly, regular maintenance and testing of the grounding system are essential for ensuring its continued effectiveness. Ground resistance measurement should be taken periodically to verify that the resistance to ground remains within acceptable limits. Any signs of corrosion or damage to the grounding electrodes or connections should be promptly addressed. In addition to these technical considerations, it is also important to be aware of the regulatory requirements that govern the installation and maintenance of grounding systems. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding, and these requirements must be followed to ensure compliance with local electrical codes. Furthermore, electrical inspectors will typically inspect grounding systems to verify that they are installed correctly and meet all applicable code requirements. By staying informed about the latest code requirements and best practices for grounding, electrical professionals can help to ensure the safety and reliability of electrical systems. Effective grounding is a critical component of any electrical installation, and it is essential to take the time to do it right. The goal is to create a safe and reliable electrical system that protects people and equipment from electrical hazards. Proper grounding ensures that fault currents have a clear path to ground, allowing overcurrent protection devices to trip and clear the fault quickly, minimizing the risk of electrical shock and fire. It also helps to stabilize voltage levels, reducing the potential for equipment damage and improving the overall performance of the electrical system. When installing a grounding system, it is important to carefully consider the specific conditions of the site, including soil conditions, proximity to other underground metallic structures, and the presence of corrosive elements. The selection of grounding electrodes, the sizing of grounding conductors, and the methods of connection must all be carefully chosen to ensure a long-lasting and effective grounding system. Regular inspection and testing of the grounding system are also essential for maintaining its integrity over time. Ground resistance measurements should be taken periodically, and any signs of corrosion or damage should be promptly addressed. By following these best practices, electrical professionals can ensure that grounding systems provide reliable protection for years to come. Finally, let's consider the role of education and training in promoting safe grounding practices. Electrical professionals should receive thorough training on the principles of grounding and bonding, as well as the requirements of the National Electrical Code. This training should cover topics such as grounding electrode systems, grounding electrode conductors, equipment grounding conductors, bonding jumpers, and surge protection. Furthermore, electrical professionals should stay up to date on the latest changes to the NEC and other relevant standards. Continuing education courses and professional certifications can help to ensure that electrical professionals have the knowledge and skills needed to design, install, and maintain safe and effective grounding systems. By investing in education and training, the electrical industry can help to reduce the risk of electrical accidents and improve the overall safety of electrical installations. In conclusion, grounding electrode systems play a crucial role in protecting people and equipment from electrical hazards. By understanding the requirements of the National Electrical Code, following best practices for installation and maintenance, and investing in education and training, electrical professionals can help to ensure the safety and reliability of electrical systems. Effective grounding is an essential component of any electrical installation, and it is important to take the time to do it right. When considering the practical application of these code sections and guidelines, it's useful to think through various scenarios. For instance, in a residential setting with sandy soil and a high water table, achieving a ground resistance of 25 ohms or less might be relatively straightforward using a single ground rod. However, in a commercial building situated on rocky terrain, it might be necessary to install multiple ground rods or even a ground ring to meet the code requirements. Furthermore, the presence of underground utilities, such as gas and water pipes, can complicate the installation process and may require special bonding and grounding techniques to prevent stray currents from causing corrosion or other problems. In industrial settings where large amounts of electrical equipment are used, the grounding system must be designed to handle high fault currents and minimize the risk of electrical noise and interference. This may involve the use of dedicated grounding conductors, shielded cables, and other specialized grounding techniques. In addition to these practical considerations, it's also important to be aware of the potential for changes in soil conditions over time. Soil resistivity can vary depending on factors such as moisture content, temperature, and the presence of chemicals or other contaminants. As a result, it's essential to periodically inspect and test the grounding system to ensure that it continues to meet the code requirements and provide adequate protection. Another factor to consider is the increasing use of sensitive electronic equipment in modern buildings. Electronic devices are particularly susceptible to damage from voltage surges and other electrical disturbances, and a properly designed grounding system can help to protect these devices from damage. Surge protective devices, or SPDs, are often used in conjunction with grounding systems to provide an additional layer of protection against voltage surges. SPD are designed to divert surge current to ground, thereby preventing it from reaching the protected equipment. In addition to protecting equipment, a properly designed grounding system can also help to improve the overall performance of electronic systems. By minimizing electrical noise and interference, a good grounding system can help to ensure that electronic devices operate reliably and efficiently. Finally, it's important to recognize that grounding is not a one-size-fits-all solution. The specific requirements for a grounding system will vary depending on the type of building, the type of electrical equipment being used, and the local soil conditions. As a result, it's essential to consult with a qualified electrical engineer or a contractor to design a grounding system that meets the specific needs of the installation. In summary, grounding electrode systems are a critical component of any electrical installation, and it's essential to understand the code requirements and best practices for designing, installing, and maintaining these systems. By carefully considering the factors discussed above, electrical professionals can help to ensure the safety and reliability of electrical systems and protect people and equipment from electrical hazards.